So we've now talked in several different ways about nuclear radiation. We've talked about the different types of particles. We've talked about how to balance nuclear reactions. We've talked about whether it's going to kill us. Now what we want to do is consider what happens over time to these radioactive particles. Because if I start with a big pile of radioactive material, and I've got all these atoms in here, all of whom can decay via radioactive processes, what happens if I wait a while? Well, if I wait a while, let's say in the case of carbon-14 or something like that, eventually they all end up turning into nitrogen-14. And what else? Do you remember what else? We've got a 6 here, we've got a 7 here, so that's got to be a 0 minus 1 beta particle. And so eventually they all decay into nitrogen-14. So at the beginning I have all carbon-14. At the end I have all nitrogen-14. But the question is, how long does that take? Does that take a really long time? Does that take a short time? And it turns out it varies quite a lot, and we'll see numbers as we go along. But it doesn't happen instantaneously, right? Just like when you pop popcorn in the microwave, you sit there for a while and nothing happens for a while, and then all of a sudden things start to pop, and they pop, and they pop, and they pop, and they pop. But it's not like all the popcorn pops at once. And if you looked at any individual piece of popcorn and just stared at it, you wouldn't be able to discern, is that piece of popcorn going to pop now? Or now? Or now? You wouldn't be able to do that. But you'd know from experience that, over time, a lot of popcorn's popping at about a minute, a little less at a minute and a half, and then there's almost nothing popping at 2 minutes because all the popcorn's already popped pretty much. The same thing kind of happens with nuclear processes. At the beginning, when there's lots of radioactive material, there's lots of different atoms that are going to be able to pop, that are going to be able to undergo radioactive decay processes. But as you get towards the end and you get towards stable atoms, nitrogen-14 is a stable atom in this case, then there's very little carbon-14 to pop, and there's not going to be much popping. There's not going to be much radioactivity going on. And so we have a lot of activity at the beginning, very little activity at the end. What happens in between? Well, what we want to talk about next is what happens when we go from all radioactive to half radioactive. What is that? And I'm drawing it one on top, one on the bottom, but that's not how it happens. It's all mixed together. It's just easier to draw one on top, one on bottom, so that's what I'm doing. What happens that, and how long does that take? Well, it turns out this has a name. The time it takes for half of the material to undergo decay is called the half-life. So the time it takes for all of this carbon-14 to turn into half carbon-14 and half nitrogen-14 is called the half-life. And it's around 5,000 years. We'll talk about the number in detail later. But an interesting thing happens. What about if I want to do that again? So I wait one half-life to do that, and I wait another half-life here. Well, half of my sample disappeared in the first half-life. Should the other half of the sample disappear in the second half-life? And when you first think about it, that might be intuitive. Let's say I had 5 grams or 10 grams, 5 grams disappeared in that first half-life, 5 grams is going to disappear in that second half-life. But you also have to think about it this way. If we start from this point, there's less popcorn. There's less carbon-14 there that's able to undergo decay. And if there's less stuff able to go decay, if there's less popcorn that's unpopped, what happens? Less popping. And so it turns out that in that second half-life, we don't get rid of all of it. We get rid of another half of it. And what you end up with is a situation where that's the nitrogen-14 we made in the first half, and then that's the nitrogen-14 we made in the second half-life, and then we have a quarter of our carbon-14 left. And every time we do a half-life, that happens, because our next half-life starts with even less popcorn, and when there's less popcorn, there's less popping. And so half-life is a constant. It's always half of what's there, not half of what you started with at some point in the past. Another way to think about it is, does this carbon-14 I'm circling right now, does it know where it came from? Does it remember how much was there when it started? And of course it doesn't, because it's an atom. It doesn't have a memory. And so it doesn't know what it started with. It only knows where it is now. And so half-life is always based off of now. And in this case, we have half as much popcorn as we started with. And so we're going to have less popping. And it's going to take the same amount of time for half to happen. And so this thing called half-life is a constant. And it's never changing for a given atom. For a given radioactive isotope like carbon-14, it's always going to be around 5,000 years. For other isotopes, it's going to be longer or shorter. And again, we'll see lots of examples of that as we go forward. So let's go and do an example, because that's usually a little more illustrative than just trying to talk about these things kind of in abstract terms. If you go and look on the internet, you'll find equations that govern this thing. There's an equation that uses an exponent and has time in it, and and you can use that equation. It'll calculate it properly. That's how people do it in real life. But what we're going to do in this class is we're going to keep it a little more simple than that. We're always going to do exact halves. And so I'm going to say that iron 59 has a half-life of 44 days. And what I want to know is, if we start with 8 milligrams of iron 59, how much do we have left after 176 days? And at first you might be like, I don't know, how am I going to figure that out? But again, what we have to do is start taking apart the problem, use what we know, and then see if that can lead us to an answer. Why is it in milligrams here? Well, it turns out radioactive isotopes aren't that common, and so if you're going to get them, chances are you have a very little amount of them. If you buy a little bottle of water, it's essentially free. You're paying for the plastic because the water's cheap. If you buy a little bit of water that has a different isotope of hydrogen in it, something called deuterium. It's hydrogen with 1 proton and 1 neutron. That little tiny bottle of water, instead of being essentially free, is now $1,000. Because these isotopes aren't very common, they're hard to isolate, and so they are a little expensive. So you'll often see people talking about milligrams, nanograms of these isotopes. The unit doesn't really matter as long as you're consistent with the unit, and then we can go from there. So what do we know? Well, the only thing I've told you so far is that half-life is a constant, and it's the time it takes for half of it to decay. So I'm going to put this here. I'm going to write down 8 milligrams is what I started with. And I'm going to put my half-life number 1. That's going to be 44 days. And what's going to be left at the end of those 44 days? Of course, right? It's going to be 4 milligrams, because half of it has disappeared, because that's what half-life means. Well, I don't want to know how much is left after 44 days. I want to know how much is left after 176 days. And so I can do a second half-life here, which is another 44 days. And for those keeping track, that's 88 days total. And what's going to be left at the end of those 88 days? Well, it's going to be half of what we started with. And you're like, well, that's not half of what we started with, but it is half of what we started with for our second half-life. Okay? So 4 milligrams to 2 milligrams in that second half-life. Well, what's going to happen after that? We're going to have a third half-life, because we're looking for 176 days and we're not there yet. We're going to have a third half-life for 44 days. 44 plus 88, that's going to be, what is that, 132? 132 days total. And what's going to be left at the end of that? That's going to be 1 milligram. Because half of the 2, every 44 days, half of it disappears. But we're still not quite there yet. And if we add 44 more days to get half-life number 4, we're going to have 0.5 milligrams. And that's for a total of 176 days. So that's how we can solve a problem like that, is we figured out how many days that took. Now, another way to do that is to figure out how many half-lives are in 176 days. So we can say 176 days, and then you get 1 half-life for every 44 days. Normally I do the units first and then the numbers. I meant to, but I got ahead of myself. And that's going to be 4 half-lives. Right, so that tells us that we have to do this 1, 2, 3, 4 times. So you can either keep track of the days as you go, or you can calculate the number of half-lives at the beginning so you know how many arrows to draw. Each one of those arrows is one of your half-lives. I could also run this problem backwards. I could say, hey, we've got 0.5 milligrams now. What did we have 176 days ago? And in that case, every time you'd multiply by 2, because 44 days ago, we had twice as much. 44 days before that, we had twice as much as that. 44 days before that, we had twice as much as that. So these problems can go either way. They can go forward and they can go backwards. So just be aware of that. I could also ask the problem, how many half-lives does it take for this 8 milligrams to go down to 0.5 milligrams? And you do the same thing. You draw each one of these half-lives, count them up, and figure out how many it took to get to 0.5. Each one of the arrows is one of your half-lives, so you'd say 4 half-lives. But all the problems that we do in this class for half-lives should have some sort of drawing that looks like this. And the only reason I went down at the end is because my screen was going. If you've got space on your paper, by all means, keep going off to the right. So every problem that we do in half-life should have some sort of drawing like this to help you calculate and coordinate what you are doing. So here's one for you. A sample begins with 96 nanograms of radioactive material. How much is left after 5 half-lives? And again, don't get tripped up by those nanograms. Just treat the number 96. The nanograms, the units, will just stick with each one of your things. Don't worry that it's 10 to the minus 9th, and that's a hard number to imagine. Just treat it like a 96, and then keep the units along. So take a chance to try to solve that one. You're back now. Let's see what you did. Did you do 96 nanograms? 1 half-life. Half of 96 is going to be 48 nanograms. Half of that, 24 nanograms. Half of that, 12 nanograms. I'm going to move down to my next line here. Half of that, 6 nanograms. And half of that, 3 nanograms. Now you'll notice here, I did put 3.0 nanograms because we did have 2 sig figs. I don't worry too much about sig figs in these type of problems just because I really want us to get the concept of half-life more than I want us to worry about the details of sig figs. So 3.0 nanograms is how much we have after 5 half-lives. So does everybody take 44 days? Well, no, because I told you that carbon-14 takes 5,000 years. So let's look at this table, which has some half-lives of some common radioactive isotopes. The top part of this one is what we call naturally occurring isotopes. These are ones that you can go out into the world and find. You dig up some dirt, you take a plant apart, you're going to find some carbon-14 in there. Its half-life is 5,730 years. That seems like a really long time. So if I have a pile of carbon-14, I have to wait 5,000 years before half of that has turned into nitrogen-14 and half of it remains carbon-14. I have to wait another 5,000 years for half of that to turn into nitrogen-14 and another 5. So it goes on. And it seems like a really long time until you look at things like potassium-40 here, which has a half-life of 1.3 times 10 to the 9th years, or uranium-238, which has a half-life of 4.5 times 10 to the 9th years. Oh, that's a long time. 4.5 times 10 to the 9th years, that's 4.5 billion years. That's estimates of the age of the Earth. And that's really neat because it means that the uranium that we have now on Earth, the uranium-238, is about half of what we had at the beginning of the formation of the Earth, which is kind of cool. So some things take a really long time. Then you get strontium-90, 38.1 years. Well, that's not very long at all. That's pretty darn fast, actually, in comparison to billions of years. But then the question comes up, well, if strontium decays every 38 years, and you start dividing by 2, and let's say the world is billions of years old, there should be no strontium-90 left. I mean, put it in your calculator, put in a big number, put in 10 to the 20th. There's 10 to the 20th strontiums. And then divide by 2 like a million times. You're going to get 0. There's none left. So is there any strontium-90 left on the planet? And the answer is yes. It's being made by other radioactive processes. So other things are falling apart in radioactive reactions, and they are forming strontium-90, which is itself radioactive. In fact, that's very, very common. Oftentimes, radioactive isotopes fall apart into other radioactive isotopes, which fall apart into other radioactive isotopes. And it's actually a very long process to get something that's stable. Now we're going to compare these naturally occurring ones to ones that are medical. So what do we mean by medical? These are used for either diagnosis or treatment of medical issues. And you're going to notice something about all these half-lives. They're a whole lot shorter. We're talking days or hours. Now, why would that be? Why would all these medical ones be shorter? Well, one, we pick them that way. Okay, so we're picking these ones with very short half-lives. Why would that be? Well, it turns out if you go and you're going to get a thyroid scan, you're going to take some iodine-131, and they're going to look for these beta particles coming off of your body, whether your thyroid's absorbing them or not. And, well, you just took a lot of iodine-131, so you're full of radiation. You don't want that radiation to sit in your body for the next 4.5 billion years. You want that radiation to get out of your body very, very quickly. And an 8-day half-life, if you wait, 24 days, that's 4 half-lives, or another 8 days, that's 5 half-lives. Already you're seeing a significant decay in the amount of radioactive material that's in your body. And in fact, if you get some of these types of tests, they'll send you home with a letter that says, hey, for the next 30 days, avoid babies and old people because you're a walking bag of radiation. No, they don't say that, but that's what they mean. Because you are. You've got all this radiation coming out of you, and you don't want to expose other people to that radiation. Another thing that happens is a lot of these things you end up just, I don't know what term to use, just peeing out. Okay, so a lot of them your body just naturally gets rid of. So those are the 2 ways you're getting rid of the radiation. Another thing that we want these very short half-lives for is if we're trying to detect this iodine-131 decaying, we want a good signal. We want lots of iodine-131 to be decaying so we can detect that. And so by having a short half-life, the popcorn pops very quickly, and we can hear that popping or see that beta particle coming off, and use that as a diagnostic test. Technetium here, 6 hours. Well, that's got to get from where it's made to the hospital really quickly. In fact, a lot of hospitals have either their own or in a building next door, they have the ability to make technetium-99 metastable. Don't worry about what the metastable means. Right next door. And so they can get it over to a patient to do their diagnostic testing very, very quickly because in a day or 2, there's almost none left, which is kind of cool. So what we're going to talk about next is an example of applying radioactive decay to a problem that people are interested in, is how old is something? That's definitely things that we want to know. We find we find a tree somewhere, we want to know, oh, when did that tree die? Or we find bones and we want to know when that person died. We find other organic matter, right? Why organic matter? Because this is carbon dating, and organic things are made out of carbon. So what do we do? Well, what we know is that there's a lot of carbon-14 just naturally occurring in the world. But again, with a half-life of 5,000 years, it can't be the carbon-14 that was here at the beginning of the Earth if the Earth is 4.5 billion years old, because there'd be none left. So it's got to be constantly created. And it turns out it is constantly created. So if we take our Earth down here, and above the Earth, there is this wonderful thing called the atmosphere, a blue atmosphere. And what it does is it protects us from all those cosmic rays coming off of the sun, which are beating down a lot of high energy things. A lot of regular visible light gets through, some ultraviolet light gets through, but most of the stuff gets absorbed by the upper atmosphere. But it turns out some of this really high energy stuff in the upper atmosphere, one of the things it does is it collides with other things and actually makes carbon-14 in the upper atmosphere. And that carbon-14 can wander around for a while until it runs across some oxygen molecules, and then it makes what we call isotopically labeled carbon dioxide, which means that carbon dioxide has a specific isotope, carbon-14, associated with it. Now, what on earth really enjoys carbon dioxide? Well, of course, that's our little green plants down here. So if we have some shrubbery down here, it's going to absorb that carbon dioxide, and now there's a bunch of carbon-14 inside that shrubbery. Inside that little tree there, it's absorbing carbon-14. So yes, the tree that's outside your door is radioactive because it's got carbon-14 in it. But wait, so does that mean we can only date things that are made of trees and plants that absorb CO2? Well, what happens? A cow comes along and eats that plant, right? So what did the cow do? The cow just ingested carbon-14. Okay, so the cow is radioactive. Well, then what do? We eat the plants, and some of us eat the cows, and so we're radioactive. So yes, we contain a bunch of carbon-14 that came from the upper atmosphere from cosmic rays hitting the planet, forming carbon-14 labeled carbon dioxide, and going down into the plant. So how do we know how old something is? Well, it turns out the sun itself is pretty stable. It's been making about the same amount of energy for quite some time, and so the amount of carbon-14 that's made up in the upper atmosphere is relatively constant. And if it's relatively constant how much is made up here, it's also relatively constant how much is absorbed into a plant. And so we know what the most common ratio of a living plant is, carbon-14 to carbon-12. It's a very small number, but we know that ratio. So what happens when this plant dies? So I don't have brown here, so we now have that same plant. It's orange, it's dead. It's not taking in any more carbon-14, is it? Right? Because only live plants take in carbon-14. So over time, the amount of carbon-14 that's in this plant decays into nitrogen-14. And so there's less and less carbon-14 in there. And what we can do is we can detect how much carbon-14 is in a dead thing, a dead plant, a dead animal, a dead anything that was once living, and compare that to what we think should be in there if it was alive. And if it's about half as much as it should be, then the thing's about 5,730 years old. If it's about a quarter as much, then it's 2 times that, which is what, 11,470 years old? No, 60 years old? And if it's 3 times that, or 4 times that, or a fourth of that, then we can figure out exactly, not exactly, but approximately how old something is. And that works for up to about 40, 50,000 years old. We can use carbon dating to do that. Beyond that, it gets a little bit hard. There's problems with carbon dating, right? If you're trying to analyze the sample of something dead, chances are somebody live was handling it, or there are bacteria coming on it, and so there's contamination issues with this. But we can get pretty good ideas of how old something is by doing carbon-14 dating. All right, so that was our foray into half-lives. We learned how to understand what a half-life is, do some calculations with it, and then even apply it to medical uses and also to carbon-14 dating. What I want you to be able to do in the class is to be able to do those kind of drawings I did with half-life and be able to figure out how long ago, or this many half-lives ago, how much was there, or this many half-lives from now, how much was there, or how long is it going to take to get from this number to this number, similar to those examples that we did earlier. Thanks.